is David Fernandez Piñas, and I'm going to present you my final project for the open source and free software master of the Universitat Oberta de Catalunya. It's a research developed with the Internet Computing and Systems Optimization Group about the design and implementation of an algorithm for the management of radio resources in satellite communications networks. Hereafter is shown the index of the presentation. First of all, the project topic will be introduced. Some key concepts will be explained. Then, the problem addressed in this research will be described. It's a minimization problem. Next, it will be commented the literature review performed at the initial stage of the research and the main issues found. In the R approach section, it will be described the new algorithm designed and implemented in order to efficiently manage the network radio resources. The results of several computational experiments performed with the implementation of the proposed algorithm are shown next. Finally, the conclusions of the research and possible future extensions are commented. The next figure shows the main aspects of the considered satellite network. It has a star topology. The terminals compete for the communication resources. Terminals convey their needs to the central hubs, which assigns them resources in order to satisfy traffic quality of service needs, using the minimum resources. Terminals can get assigned three types of resources: radio frequency bars, depending on the current link budget, which can be bad, average, or good. The period of resources assignment can be dimensioned analytically, following some considerations. The selection of a resources assignment period multiple of the shortest bus duration eases the resources management. As the considered system is based on multi-frequency time division multiple access, periodically the available time and bandwidth must be assigned to the terminals. This can be done following a structured approach, where the available spectrum is first divided into carriers, then the frames of the carriers are assigned. Or it can be done following an unstructured approach, assigning directly chunks of bandwidth and time anywhere, as shown in the right part of the figure. Unstructured approach is less optimum in the usage of resources, but minimizes signaling required to communicate the assignments to the terminals and requires less computational resources, while unstructured approach allows the maximum optimization but makes the problem computationally hard. 5 traffic profiles have been generated to perform the research. In each file, the arrival of requests for capacity at the network hub are described. Each request is of one of the three types of bursts shown before in slide 4, and it has an associated expiration time. Somehow, the traffic profile can be represented as falling blocks of a Tetris-like game. If the needs are not allocated resources before they reach the floor, they are lost. If the transmission timeout is lower than the assignment period, the allocation of resources to a need is mandatory. Otherwise, it could still wait to the next allocation period. The problem addressed is how to minimize the bandwidth required to satisfy all the communication needs specified in the considered traffic profile, but also trying to keep low the size of the resulting burst time plan, BTP, required to communicate the hub assignments to the terminals and respecting some additional constraints, such as the one that having only one transmitter per terminal. Before starting to search a way to solve the mentioned problem, a literature survey was performed in order to check if this problem had been addressed before and how. Several papers were found addressing the topic, but for best effort data traffic without strict delay constraints, and all the papers found discarded unstructured approaches. Due to the mentioned reasons in slide 6, one of the found papers proposed the use of packing heuristics for static on-demand assignment of resources. Not each few milliseconds, and it's in our case, but previous experiences in the operation research field made us suspect that a not-so-complex packing heuristic could be used also in our case, with assignments each 260 milliseconds. Because of this, a literature survey on two-dimensional strict packing algorithms was done, in order to select the heuristic that would be better for our problem characteristics. The literature research went further to meta-heuristics also. This has given us ideas for future expansions of the research, in terms of the use of randomization and parallelization. As it has been mentioned, we propose an structured approach for solving the problem, but in order to minimize the signaling required, the frequency hopping of terminals is minimized when assigning resources by aggregating contiguous need from a single terminal. The best fit decreasing height heuristic is selected to solve the problem after it's found in the literature survey that it can be used to place thousands of rectangles in hundreds of milliseconds. Finally, just mention that the scheduling of pending transmission needs is done according to an earliest deadline first policy, which is considered a very efficient one in the telecommunications literature. What follows is an explanation of how the design and implemented algorithm based on the best fit decreasing heuristic works. The arriving transmission requests are checked each allocation period, SFT. They can be represented as following blocks in the time dimension. Blocks from the same terminal are piled in columns, one per terminal. The solid rectangles are transmissions which timeout has exceeded the so-called obliged transmission threshold, so they must be allocated in the next assignment period, while the outlined rectangles are transmissions that can still wait until the next period. The minimum possible value for the obliged transmission threshold is the allocation period, but it's convenient to make it higher to avoid packet losses due to transmitter overload, which can happen due to the arrival of a packet with a short expiration time after a big packet with a long expiration time, which transmission has been excessively delayed due to a very low value of the obliged transmission threshold. Once collected and aggregated, optional and mandatory transmissions are stored in two vectors, ordered by decreased in duration. The so-called floor burst vector contains the transmissions starting at the beginning of the assignment period, and the floating burst vectors contains the transmissions that follow another previous transmissions that it has not been possible to aggregate because of having a different bandwidth. In order to minimize signaling, just assignments for transmissions with the same bandwidth from the same terminal are aggregated. The results show that just a few assignment periods have floating bursts, as the case shown in the figure, which has two floating bursts. The floating bursts are bottom left packed to the floor burst. If this initial packing results in a bandwidth occupation higher than the current maximum bandwidth configured, the packing based on the best fit decreasing heuristic is performed. Otherwise, the assignments are considered done. The best fit decreasing heuristic is applied first for the packing of mandatory transmissions, which will determine the minimum bandwidth required. The remaining resources are filled afterwards with optional transmissions, applying also the best fit decreasing height heuristic. The packing is obtained by placing the transmissions from down to top and in columns, forming levels. In order to minimize the signaling required to communicate the assignments to the terminals, in our proposed algorithm, just items of the same bandwidth are placed on a given level. If this cannot be done, a new level is created. Notice that on a real system, the algorithm should discard mandatory transmissions if they need more bandwidth than the one available or configured, while in our implementation, it results in an update of the maximum bandwidth use result, because our objective was the study of algorithm performance, not just an implementation of an algorithm for a system. The figure in the slide shows a resulting packing with our algorithm. Although the algorithm has been implemented as a C++ application, an open console application, an OpenGL-based viewer has been developed so we can see it in action from traces generated by the console application. Hereafter is shown a 5-minute extract of viewer output for file number 3 with the obliged transmission threshold configured for not having packet losses. The viewer stops its from time to time when an assignment that results in an update of the maximum bandwidth happens, or when there are floating bursts, which is something that will not happen. Otherwise, it will run continuously, increasing the assignment period counter. The figures show the allocations performed in the period of maximum bandwidth use for the cases of configuring the obliged transmission threshold with the maximum value found in order to have a packet loss rate of 0 packets. Hereafter are shown figures indicating the resources utilization efficiency in function of time for file number 1, minimum load, and also for file number 3, which has the maximum load in the right. It can be appreciated that the resources utilization efficiency increases with the traffic load. The resulting minimum bandwidth does not seem to depend on the obliged transmission threshold configured, as shown in the next figure. The same happens with the resources utilization efficiency. This figure shows how the packet loss rate due to overload diminishes as the obliged transmission threshold is increased. This research has produced, in our opinion, a novel approach to the radio resources management in telecommunications networks, especially for time-constrained traffic, by adapting an algorithm from operation research to telecommunications, implementing it and demonstrating its performance. In the future, it is expected that the application of randomization and parallelization could lead to even more optimized results compared to this first deterministic version. And that's all. Thank you for your attention.